I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows my God.
With thanks to Wing Ying for inspiring this event, a Wonderfest patron, please welcome Dr. Peter Norvig.
Okay, thanks, Tucker. Great to be here.
You'll man the door.
All right, and go see Lynn Rothschild. I work with her at NASA, so she's going to be great. So here we are in the middle of Silicon Valley, where this gigantic software industry has grown up. Who would have guessed it? When I was in school, I said, this computer stuff is kind of fun, and I'll do it because I like it, and never would I have imagined that it would have ended up like this. Right? So we've been able to do so much with the hard labor of men and women and sometimes kids who build stuff with their raw hands that turns out to be useful. But now it seems like maybe we're approaching it with a different take, to say maybe it's not going to be all hand labor. Maybe we can learn programs automatically. So how would that work? So here's the traditional model. Here's our hero, the programmer, who gets an idea and then thinks out all the possibilities and writes them down using some obscure programming language, and has to have all those ideas in the head and get them right. And so that makes software basically a mathematical science. It's logical and it's certain, and we know that kind of in the limit we could prove our program's correct. And of course we never really end up doing that for anything longer than a program about this big. But we know that that's what we're aiming for, and we sort of prove a few little properties out of them. But in order to get there, every step of the way, every part of that complicated flowchart has to be programmed by hand. And essentially that means our programmer is a micromanager. And nobody likes to be a micromanager, and nobody likes to be micromanaged. Now, what's the alternative? So in machine learning, the thing that's going to write the program is not the human, it's the computer. The computer itself is going to create a program that does what it's supposed to do. Now, there's still employment opportunities left, so there is a human in the loop, but they're no longer a programmer, they're essentially a teacher. So how do they teach the system? By gathering some data, showing examples, and essentially saying to the computer, do more like this. And the computer writes the program, but it doesn't look like a traditional program. Instead, it's this black box, and I've very optimistically shown the black box with the top open, so maybe we can peek inside and understand a little bit about what it's doing, but we don't have the same level of understanding of it as we do from inspecting the source code that we wrote by ourselves. So the human's role here is very different, and we've ended up now we're making software not a mathematical science, it's more of an empirical science. And it's based on probability and based on uncertainty rather than on Boolean logic. That means, we're sort of like a field biologist who goes out, observes the world, makes some theories, runs some experiments to test those theories. You're never quite sure because there's error bounds and p-values and all these things on your experiments. So you don't know if you have it quite right, but you can do things that you couldn't do before. And now the model of what a programmer is, you're no longer a micromanager. It's more like being a teacher, that you're showing the computer what to do rather than telling it what to do. And I think General Patton knew what I'm talking about. He says, don't tell people how to do things, tell them what to do, and let them surprise you with the results, right? So people can be inventive, computers can be inventive. Now, so I started off talking about the software industry as a whole, and we've come a long way, right? So we started out with sort of the studio model. Here's two guys named Steve in their garage, and we didn't know much about how to build software, and so, you sort of had to be an artisanal expert in order to accomplish something. But we said, well, that'll never do, because there's only so many guys named Steve. So we came up with a factory model where we put people in cubicles, and now we can have large teams that could do things that we could never do before. We can do things that are much larger. but maybe it's not so much fun being in the factory model. So now with machine learning, it's more like the school model of we're going to teach these machines how to do the right thing. All right, so it's a different model. The whole process is going to be different. Why would you want to do this? And I think of three main reasons. So one is you can produce software much faster. And here is the logo for Google Translate. And we built this system, and we built it at a time when the competition was saying, yeah, we can build machine translation systems. And the way we do that is we hire a whole team worth of linguists, and they write down rule by rule, here's how English grammar works. The sentence is a noun phrase and a verb phrase, and here's the definition of every word. And it's going to take them a couple decades worth of work to do each language, or each language pair, French to English, say. And we said, well, that's great. We could contract your services for that. But we think we really want to do about 100 different languages translated in between all pairs. That's 100 times 100. It's 10,000 languages. 10,000 languages times a couple decades each. We didn't really have that amount of time. So we said, what if we build one system that can take two language pairs, you drop them in, and it automatically learns. It might take us a little bit longer to build that one system, but once we've got it, now we can instantly go from 1 to 10,000. So it's this speed up factor. Another thing is this kind of magical factor that I can now do. It's not only, so I could have theoretically programmed that translation system. I kind of knew how to do that. But there's other things that I don't know how to do as a human. So say just recognizing faces of my friends, I can do that as a human, but I can't do that as a programmer. I couldn't write the code to distinguish one person from another. But I do know how to write a machine learning system where I can show it examples and it will automatically pull that out. Right? And so that's what we've done many times and things like that. So we're getting really good at image recognition. And I take a lot of photos, and I can't tell you how much time I wasted organizing them into folders and putting keywords on them. And now you just drop it all into the machine learning system. It does it all for you. In fact, my friend was telling me the other day, he said, I finally took the plunge into Google Photos, and I got all my digital photos. That was easy. And I got all the old analog photos, and I got them scanned, and I uploaded them. And now it's great. I say birthday party, and it just fetches them all. I didn't have to label them or anything. And he said, but we have a bunch of sort of the best photos, the ones that we really love, but when our kids were really small. And he said, I was searching for one of them, and I couldn't find it. And then I finally found it, and it had labeled Michael as William. And I said, oh, that's funny, I screwed that up. And then I looked closer, and I said, wait a minute, Google was right. And all these years, we had been loving this photo, and we had it wrong. Right? So we can do these things that you couldn't do by hand. So that's number two. And then the third reason is continual updates, and it's kind of a different version of faster. Right, so things like fighting spam. So we have to do that for email, we have to do that for web pages, and the bad guys are always trying to defeat the system. The problem is, as soon as you shut them down, they realize they've been shut down and they try something new. And now you've got to go back and counteract that. And if you had to have a human in the loop every time that happened, you'd always be behind. But a machine learning system, if you do it right, can respond at sort of the second by second level rather than the day by day or week by week level. Okay, so those are the three reasons you want to do it. Let's see some examples. So of course, playing Go was considered a tough game. Decades ago, we had figured out how to play chess, but there were fewer chess moves, and it's kind of easier to tell who's winning a chess game. Go was considered very hard, but it turns out the methods we have now are able to conquer that game. We do a lot of work of managing complex systems, right? So we have data centers around the world. There's flow of information back and forth. We want to know the most efficient way to cool them and so on. And there's just too many variables to keep track of. You throw them all into a learning system, it comes up with a plan, and you save millions of dollars worth of efficiency. Now, I said that we were sort of making this transition from logical and Boolean, it's either yes or no, to probabilistic and uncertain. And that's true even in the ways we interact with our computers, right? So it used to be you interacted by pressing on a keyboard, and you either pressed one letter or you didn't. And now it's not so much that way, right? So a lot of the time we're talking to our computers, and that's always going to be uncertain, what did you say? And even when we're typing, we're not hitting physical keys anymore, we're swiping around on the keyboard. And on the left there is two different paths for two words, and I think, let me see. So I guess one is value and one is vampire, right? And so those are two very different words. You wouldn't want to mess them up, but the path that you swipe through is pretty much the same. And as a human programmer, I wouldn't want to have to say exactly where is the boundary of when you call it value or when you call it vampire, and for every other possibly confused word. But machine learning can pick that up. And on the right, similar kind of thing, but here we're joining English and German and French all into one, and it's figuring out when to switch back from one to the other. Here's an example of looking at images of retina and diagnosing diseases, and we've had some good success there. Here again is the machine translation combined with the image recognition. So you point your phone at a sign and it translates the sign, and it even picks out the right font and color for the translation. And we make a lot of these things available as services. So you can come in and upload pictures and get back a description of what's in them, and you could build your own services on top of that. It turns out 17-year-old kids are doing it, using our software, diagnosing breast cancer. Graduate students are doing it. So these are two physicists who wanted to understand gravitational lensing. This is this idea that there's two galaxies out there, and the light from the farther one gets bent by the gravity of the closer one. And if you could understand exactly how that worked, you could essentially weigh this galaxy and figure out how much dark matter is in it. But the physicists only knew how to do that in the forward direction. If I knew what these galaxies were like, then I could see what light would show up on my telescope. And we want to do it in the backwards direction. I got the light. What could the galaxies be like? And these physicists said, not knowing any machine learning, says, I think these deep learning networks can do that. They can go in this backward direction, and they have this property of being differentiable, which means you can back propagate. And so they said, that seems like a good match. I don't know anything about it. But in 2 months, they figured out how to make it work. It's just as accurate, and it runs 10 million times faster. Now, that seems awesome. On the other hand, these are physicists, right? So dealing with math is not hard for them. They got to step up. So it doesn't mean that everybody can do it. Here's an example where we said, let's combine the vision stuff we're doing with the language stuff we're doing, and take the task of coming up with a caption for a picture. And that's a good task because we've got lots of examples, right? So machine learning works by showing examples. There's lots of examples we can get of images on the web where there's a photo and a caption that goes with it. We can train a system. Now we show it a photo it's never seen before, and we say, come up with a caption, and it says, 2 pizzas sitting on top of a stovetop oven. So maybe not exactly the words I would have chosen, but pretty amazing that it's a grammatical sentence in English. It's picked out mostly the key ideas, and basically it's gotten it right. So it's learned vision and language and kind of the task of captioning all at once. Now, I could show you more impressive stuff like this, but it's really more fun to see the outtakes. So we have a system internally where you can upload photos and get the caption back. And then off to the side, there's a place where people store the ones that they thought were fun. So here's one. And the caption was, a couple of giraffes standing next to each other. I'm not sure where the couple came from. I think that's just an indication of I'm confused. But the giraffe kind of makes sense because, even though we've shown this thing billions of pictures, I've never seen a horse in purple pajamas before. And the spots on the pajamas maybe do look a little bit like a reticulated giraffe. Here's one. Reflection of a dog inside your mirror, right? So objects in mirror are larger than they appear. Here's a nice picture. It says a man riding a skateboard. And I don't know how well you can tell from the projection there, especially in the back, but there are parallel lines in the floorboards there that maybe do look a little bit like the deck of a skateboard, but there's certainly no wheels. But somehow the computer imagined that nobody, even the king, would be in that pose unless they were riding on a skateboard and losing their balance. So we can do that. Of course, there's the self-driving car work. And companies like Google has put many, many years into this, and have, so here you show sort of what the car's got to figure out about its environment. But I think one of the fascinating things is we're now seeing a much faster path to making something useful, right? So here's another self-driving car company called Voyage, and they're operating down in San Jose. And what they said is, we're not going to do that much research on our own. We're basically going to take off-the-shelf technology. We know the technology isn't quite ready yet, but what we're going to do is we're going to drive it in a controlled situation. So they've deployed their fleet in a retirement home, retirement community. And so there's only, I think there's 20 miles worth of road, and those are the only places it's going to drive. And there's a speed limit, which is slow. So if they get in trouble, you just pull over to the side and stop. So they don't have to solve all the really hard problems of self-driving technology. But what they're doing is basically making a good application that will be useful within a limited domain. And I think we'll see a lot more of that. As the cutting edge moves out, there'll be people following just behind the cutting edge that says, I've got a niche application that doesn't have to solve all the problems, but I can carve out a small subset of the problems where it'll be really useful. Okay, so you probably all heard this idea of deep learning, and the question is, what does it mean? And maybe you've seen pictures like this of some mystical stuff. So first of all, if it had been up to me, I wouldn't have used that term. Right, I probably would have called it hierarchical basis function regression. So you can tell why I'm not in marketing, right? So what does this mean? So hierarchical means in machine learning, what we're trying to do is build this black box, and you give it some inputs, and we get some outputs. And we could go directly from the inputs to the outputs, or we can go in multiple steps. So basically, the output of one box feeds into another box. And hierarchical just says we're going to try to do that in multiple steps. Well, why is that useful? Because in each intermediate part, we could be producing some new output. Rather than trying to go in one step from the inputs to the answers, we say go from the inputs to something you've learned about the inputs, to something more you've learned about that, and then go to the answer. And sort of at a theoretical ultimate level, if I had an infinite number of input, it wouldn't matter whether I was hierarchical or not, because it could still learn the same thing. But with a limited amount of input, by putting sub-boxes around the sub-pieces, you're constraining the network and giving it a better chance to learn these intermediate values. So that's what hierarchical means. Basis function just means I'm going to have a lot of little pieces, and I'm going to combine them by adding them up. And then there's a little part that's not quite adding them up. And regression means predicting, doing the best prediction you can of what the output value should be and trying to minimize the error. Okay, so that probably doesn't tell you very much. So let's do an analogy. And imagine I've got a business of selling these kitchen tiles. And I've got a catalog with a bunch of pretty pictures like this, and you can choose the one you want. And now I say, okay, we've been running this business for a long time, but it's time to get into the modern age. What we really should do is not just have a fixed catalog of these are the scenes, we should have an upload button where you can give me your picture, and we'll make the tiles, we'll ship them out to you. So that proves very popular. But the guys in inventory say, this just isn't very cost effective, because every time we get a new picture, we have to make tiles in a one-off shot. That's not going to work. How about if we just had an inventory of tiles? Now, when a new picture comes in, we pick from that inventory the component tiles that are close enough, right? So we want the picture to look like this. And that'll be much cheaper because we can make lots of them at a time. Everything will be great. And now the question is, what should the inventory be? Right? And the answer is, it should be pieces of the stuff of pictures we're likely to get in the future. And what are the pictures we're likely to get in the future? Well, maybe they're like the pictures we're likely to get in the past. So either go to what we have, or we go out on the web and say, what does the world look like? What pieces are there? What pictures are there? And then there's a bunch of fancy math, which I'll just skip. But basically it says, if you give me a certain amount of inventory, and I want to pick the pieces that will best combine to make the best mosaics, how can I do that? And it turns out there is a mathematical answer to it. But it's not important, right? The main thing is, I'm going to pick out the pieces that most represent the world, that are most common. And, you know, that doesn't have to be an exact match. It just has to be close enough so that when you look at the tiles, you say, yeah, that looks more or less like my picture, right? So around 1996, as we started doing this, and researchers started saying, let's solve that math formula, and let's say, what is the world made out of, right? So a very exciting thing. We can get the answer to what components can draw all the pictures in the world. And here's the first answer. It came from Bruno Olsheisen at Berkeley, go Bears. And the answer was this, that the world is made out of lines. So that's kind of disappointing, right? Because I knew that in kindergarten. You gave me a crayon, and I can make pictures out of lines. But basically, this was the right answer of saying, if I want to build up a picture by having components, then having some straight lines, some diagonal lines, some vertical lines, that's kind of the best thing you can do. Not very promising. And then, as a field, we had the bright idea of saying, well, what if we go hierarchical? What if instead of just having one inventory, we build that up and then take the small pieces, build them into larger pieces, and into larger pieces still. And then around 2006 or so, we started to get this breakthrough. And now when we do that same problem, the first inventory looks the same, but the next couple levels really start looking interesting. And here I fed it a bunch of pictures of faces, and at the second level, it recognizes that eyes and nose and ears are part of the world. And at the next level, recognizes faces as part of the world. And you go up a level after that and would recognize like body shapes and so on. So this is a pretty amazing thing, right? Because I didn't tell it anything about biology. I didn't tell it what to look for, and it just found them. And basically the reason it's finding them is the photographer's fault, right? So cameras aren't just random. The shutter button fires when somebody says, I found something interesting. And something interesting tends often to be, say, a face, right? So it's getting a biased view of the world, but it's getting the view of the world we want, right? And basically all machine learning is like that. You gather up this data that has some view of the world, you solve some fancy math equations to say what are the most important parts, and then you say, if we assume the future is going to be like the past, I can make predictions. Okay, so what are some of the challenges of this approach? So you've seen some amazing things. We can drive cars, we can label all your photos, we can recognize speech. How is this different, and how does it change the way the software industry works? So one of the big challenges is this lack of abstraction barriers. So what do I mean by that? So when I look at a program, I can understand that it's in pieces and there's a flow from one piece to another. And if there's a bug here, I can start a process of saying, okay, let's take the pieces one by one, and I can say, oh, look, in this second little box here, if I feed in the right input, it gives me the wrong output. That means I know there must be a bug somewhere inside that box. And if I fix that, then I'm strictly going to make things better. There might be another bug someplace else, but at least I know I'm free to fix that within that box. But with machine learning systems, it's not like that, because there aren't separate boxes that only have one or two connections to the other boxes. Rather, everything is connected to everything else. And so you try to fix one thing, and now you've broken other things. And so we need a new set of tools in order to deal with that. It's harder to debug, and it's hard to explain sort of where the bug was. So basically, I think we need an entire new tool set. Now, I'm old enough that when I started programming, they gave me one of these, right? So and some of the old people here are nodding. So I got a pencil and paper, and we drew out, here's what the flow of the program looks like, and that was useful. Since then, the software industry has gone on and created much cooler tools. But the machine learning industry is just getting started, and we don't have those tools set yet. So we have enthusiastic people who can build systems, and by the seat of their pants, they can try to fix them up. But we're back in Steve Jobs' garage saying we're doing this just because we have experience, but we don't have a set methodology yet. And that's what, as a field, we're going to have to develop. Next, we have this fancy word we call non-stationarity. It really means the sands of time, which is we made this assumption that our predictions are going to work because the future is going to be like the past, and that doesn't hold for very long sometimes. The world changes out from underneath us, and now the system that we built is no longer any good. And we have to continually keep monitoring that and updating it and saying, when should I throw out the old data? Should I start over from scratch? Should I just gradually count the old data less? But, you know, I've gone a full year, and maybe it's really important to know what happens at Christmas time, right? So all my customers are going to act differently that week, and knowing what happened a year ago is important, but knowing what happened 6 months ago is probably not important. So all these factors we have to figure out. As data becomes more important, there's these issues of privacy and security, right? So now it's the primary asset you have is not a program, it's the data, and if it comes from your customers, there's more responsibility on you to be good stewards of that data. There's these issues of fairness, of what is it that we're really trying to achieve, and what does it mean to be fair? So let me go into that in some depth. So let's say I'm building a system, and let's say a speech recognition system, right? And so I try to make it better and better. And then my engineers say, you know, we don't have any more ideas for how to make the whole system better. But if we divided our customers up into groups, then maybe we could do something specialized for each group. And that would give us an improvement. So you say, okay, I got a certain amount of engineering effort, and now let's say they figure out, well, you know, men and women voices are generally different. So if we worked on them independently, we think we can make more progress. Now the question is, I've got 100% of engineering effort. How should I allocate them to these two groups? That seems pretty clear here. I should give 50% of my engineering effort to each group because the groups are equal size. That's only fair. Everyone could agree on that. Now, let's say there's two groups of unequal size. And it could be unequal on any factor. You know, say it's the length of the larynx means there's some special property about speech recognition. But now I got one group that's 90 million people and another group that's only 10 million people. How do I allocate my engineering effort then in a way that's fair? So one idea of fairness is per person fairness. So 90% of the effort should go to 90% of the people, 10% of the effort should go to 10% of the people. And if we do that, the total benefit, sort of multiply things out, we get 82 units of total benefit. That seems pretty good. The other thing we could say is, well, what's fair is what's best overall. Maximize the total output. And that says we should do a 100% job of finishing up the big group first, because there's more people that benefit from each unit of effort, and only when we're done with the big group should we then move on to the smaller group. Then we actually get more total benefit. So if you think total benefit equals fairness, that's the thing to do. If you think ignoring 10% of your population is unfair, then that's not the thing to do. And then finally, we could stick to what we did before, saying, well, we're going to do everything 50-50. There's two groups, so they should each get 50% of the effort. Now the total benefit has actually gone way down. And there's also an issue of, well, you're going to do that because I split the group up that way. What if I then took the big group and split it in half? Does that mean they only get a third each? And sort of these arbitrary decisions of where the groups are now have a big effect on where the effort goes. And the problem is there's not an answer to this, right? So all these other things, I skipped all the mathematical formulas, but they all had definitive answers of what the right thing to do is. Here, nobody's telling me what counts as fair. That's something that we as a society have to do, right? And so we built this math, and so this is the only slide I'll have with some math on it. It doesn't really matter. But essentially it's saying that what machine learning has come to be today is kind of the same thing that economics was. We say that both of them are around maximizing expected utility, how to do the most total good. And there's a formula for that, and we can solve for it. And it used to be that was the answer. And the only thing we argued about was, well, what are the cool techniques I can use in order to maximize? But now, more and more, we're saying maximization, maybe that's the easy part. The hard part is deciding what is it that you want to maximize, right? So what is my heart's desire? What am I aiming for? I've got to be able to decide that before I do the maximization. And that's something we haven't been trained to do, right? So computer scientists don't take a lot of classes in sociology of what would be fair for society, right? And we're going to have to start having those types of conversations. Now here's two scholars, and they had that conversation. So Mick's more famous for saying you can't always get what you want, but you get what you need. But in this case, I think Mick's got it wrong, and I'm going to go with the Nobel laureate. Right? So Bobby says, your debutante knows what you need, but I know what you want. Right? So what's the difference? Well, these are the things that we need. I think we can agree as a society, and maybe people have slightly different views on exactly how to prioritize these various needs. But we built a system where there's a marketplace in which we express our wants rather than our needs. And then the marketplace, we're kind of voting with our actions. And we've said loud and clear, these are the things that we want. And so that's what we get. And it's a sort of this virus type approach of I play Angry Birds for I don't know how many hours. And then I say, oh man, that was stupid. I wish I had those hours back. But it's too late. I can't get them back. And not only is it too late for me, it's too late for all my friends, because every click I made was a recommendation and it got pushed on to them. And then they started playing it and they started pushing it on to their friends. And pretty soon it's an epidemic, right? And we've built this marketplace for our attention so that we can decide what we want, but we built it in a way that ignores or isn't really focused on what is it that we actually need. And so, I talked about a lot of technical aspects of how we have to make machine learning and software engineering better, but underneath that all, we have to decide what we want as a society. Why don't I stop there and open it up for questions?
I enjoyed the presentation. Thank you. So you mentioned about explainability or lack thereof. So are there any progresses towards that to explain what's happening in the middle layers of learning?
And so people talk a lot about explainability. I would rather talk about trust than explainability, and I think explainability is one aspect of it. And certainly there are things, again, a lot of the research has been done on images, and some of the best learning work is done there, and some of the best kind of explainability, because it is visual. And so we can say, you said this was a cat, what made you say it was a cat? And we can sort of highlight the pixels that were most important and say, which pixels, if you changed, would have changed your decision. And so that's kind of visual. But a lot of these other things, it's much harder to do that. Now, one thing I think is we should recognize that making a decision and making an explanation are two separate things, and maybe we shouldn't be asking one system to do all that. Maybe we should train these two separate things, right? So one gives the right decision, then another one is an expert in giving explanations, and maybe we can do something like that. And I think so one way you demonstrate trust is by having an explanation that people can follow along with. Another way you demonstrate trust is by getting the right answer a lot, and people learn to trust you more. Another way is, so we have this group we call STP, Security, Trust, and Privacy, and we think they're all part of the same, right? So even if you can explain yourself, if you can't prove that you're going to be a good steward of people's data, they're not going to trust you. And then I guess another issue with explainability is often you get an explanation, but how are you going to evaluate if that explanation is any good, right? So you go to the TV news, and anytime there's a controversial issue, you've got two experts on, and they each give an explanation, and they say the exact opposite thing. And furthermore, you knew what their explanation was going to be before you asked them, right? So you knew what they were going to do is say, I have a preconceived prejudice, and this is what I think the answer should be. And now I'm going to fetch all the facts that I know that support my answer, and I'm not going to mention all the facts that go against my answer. And that constitutes an explanation, right? So that's not very good. So maybe we could do better than that, and we could demand that systems are not biased and just choosing the facts on one side, and we could demand they be fair in some way. But an explanation alone isn't going to be enough. So another aspect is, coming up in the next few months in Europe, there's this GDPR, General Data Protection Rules, that's being implemented, and one of the aspects there is explanation. And the idea is if there's something important, like I apply for a loan, I deserve an explanation if I get turned down. But say, I apply and the explanation is, well, you didn't have enough collateral. How do I know that explanation is correct? How do I know they didn't just like my skin color or religion or something? Well, from the explanation, I can't tell. But if I said, well, I want to audit all the decisions you made, not just my decision, but decisions across everybody, and now let's examine it by demographics, then I can tell if they're biased or not. But I can't tell from the explanation. So I think an explanation is part of gaining trust, but not the only part. Yeah.
You were talking about the little cars driving around the retirement home, right?
Yeah.
And my question is, my assumption is that in those opportunities, they could collect data about what's working and what's not. Low risk, but you could still find out, 3 trees, we took out this week.
Yeah.
And you could theoretically keep that data, and then the learning could continue in that low risk environment. Is that happening a lot?
Yeah. So I think that's the idea. And, all these systems sort of work at two levels. Most of the time you want to drive saying, I've got a map of the world and I'm following that map, but sometimes the map changes out from underneath you, right? And so one of the innovations Google did was say, we're going to have a very detailed map. So not just where does this road curve, but where is each of the dotted lines on the road, right? Because one problem that turned out to be pretty hard is telling where red lights are in a city environment, because the shops have lots of red lights in them. And is that a traffic light or is that a shop light? Well, the way you can say now is, all right, I'm looking at the road and I know there's going to be exactly 2,037 stripes, and then there's going to be a traffic light right there. And so I count down, I get there and I look and I see it. But if you look and the traffic light is no longer there, it's under repair, now you have to fall back on what do I do for my general purpose without that information. So any system's got to have both. But I think you're right that if you're in a smaller, more contained domain and you got pretty good coverage, if you got multiple cars driving the same place, then most of the time you'll be driving in a place where another car was just there a few minutes ago. And so your data will be no more than a couple minutes out of date rather than potentially days out of date.
My question is about AGI, artificial general intelligence, like comparable to human. How far do you think we are from that? If you personally interested in that and working in that direction, and what way do you prefer, or what way you think will actually happen to create it?
Yeah. So I guess I don't think about it much in that way, right? So I say there's lots of different things that people can do, and some of them machines can do much better, some they can do about the same, and some they can do worse. And so I don't want to so much duplicate human intelligence, right? Because in some cases that would be limiting. The computers can play Go and chess much better than people can. And for many, many decades, they could multiply big numbers much better than people can. So I don't want to duplicate human intelligence. And also, we know how to make humans. My wife and I did it twice, and I got to admit, she did a lot more of the work than I did. But that worked, and we don't need more humans. What we need is tools to help humans.
But a lack of common sense.
Yeah. So I think I still want to break things down in terms of what are the tasks and what do I need to do this task. But you're certainly right that there's some tasks I want to do that require this mix of some that's very specialized, but some is very general, right? And people talk about sort of the McDonald's employee question of here's somebody who's not trained with very many specific skills, but if there's a spill of food in a way that's different from any spill that ever happened before, they can still clean it up, right? And so I think we want to get to that level. And there's a lot of work going on in that. We have a project where we have a room about this size, which is filled with robotic arms. It has a little tub, and we just go out and gather every kind of object we can think of and dump them into the tubs, and the robotic arms spend all day sort of picking it up and seeing what it feels like and getting more and more experience of, how do I grab this thing? Well, I'm probably going to grab it here, and it'd be weird to grab it like this other way or something. And they just start learning. And, each individual action is specialized, but if you do it, a few million times, then you start to get closer to this idea of generality. And I think we'll see that in more and more areas.
How soon? General.
I still don't want to talk about it as being general, right? So I want to say there's going to be, people are going to build tools for specific tasks, and that will get better and better, and it's hard to predict how long it's going to take.
I generally don't want to divide humans or machines or algorithms, but just for the sake of my question, it sounds like the algorithms or machines actually are trying to understand humans in a much deeper level in a very, very fast speed. How is general humans making progress of understanding machines in a way like, how can we even understand what is going on in all those multiple layers, or the box and the black box? And in the future, what kind of general understanding or knowledge a newborn baby, when they're growing up, they need to grasp to kind of live in the future? Maybe they don't need to learn anything. Machines are learning everything. They're doing everything. They're programming themselves. What do biological means need to learn or to equip itself or themselves to live in the future?
Yeah. So I think we need to develop a better common language, right? So right now, when we're trying to understand what is it that the machines are doing, we give it a bunch of test cases, and we can sort of plot out what did it get right and what did it get wrong. We can sort of probe the edges of that, of saying, well, you got this one right and this one wrong. How about something halfway in between? Did you get that right? So you can sort of begin to map out what it can do and not do. But, and I talked about this idea of, looking at the pixels and saying which ones were important. So you can say which factors were important in making decisions, but you're still a long way from really understanding it. And I think what we need is a communication language between humans and machines, right? Because right now, if I'm trying to debug a machine learning system and I show it a picture of a cat and it says dog, what can I do? Well, mostly what I do is I say, okay, it's bad on the cat versus dog distinction, so I'm going to go out and I'm going to get 10,000 pictures of cats and dogs and label them and show it to them. And then I'm going to test it again, and probably after that additional training, it's going to do better. And that works, but it's kind of slow and laborious, and it feels like you're not getting at the point, right? So what I'd rather do is say, oh, you said that was a dog, but look at the ears here. I think that's pretty important. Cats have pointy ears. You should have gotten that. And then maybe the system would come back and say, oh, well, yeah, I noticed the ears, but here's why I thought it was a dog anyways. And then I'll say, no, that's not right because of this. And we'll have that kind of conversation. Right now, we can't have that, right? Because it doesn't have any way of taking that side channel of advice.
So will it be more like visual language based, or it could be something more direct connection with the system?
I think it will be a mix, right? So some will be visual, some will be spoken English language, some will be, manipulating a computer interface and, looking at plots and data and graphs of the output. And but as long as you can say, I think this part is important, and there'll be a variety of different ways that you can specify what this means. But you want to be able to say, I want to guide you in this direction, not just by showing you an example of cat versus dog, but by saying, here's something you don't know that you should learn.
How about direct implants of human interface?
Yeah, so there's certainly a lot of work in that, these brain-computer interfaces. Right now, a lot of that work is around correcting failures that people have. So people that have been paralyzed or have had strokes and so on, you want to give them the ability to do things, and you can do that through computer interfaces. And there's at least two paths. So some people are saying, well, we're going to give you a prosthetic arm, and then you'll learn how to operate that arm by having signals from your brain going to the electronics of the arm, and brains are pretty good at learning, so eventually you can learn how to control it. There's also work to say we're going to try to restore your brain, right? So patients that have had strokes or some sort of spinal injury, say, what's the difference between your brain and a normal brain? And then we'll give electrical stimulation to your brain to kind of try to train the cells that are more or less offline to have them come back and do the function they used to do. And so that's at least two approaches towards that.
Yeah, I have a question about kind of like quality control. I think with regular programming, it's pretty transparent, that, anybody can step in and figure out what the, once told by the programmer what the input versus the output is, anybody can step through an algorithm and say whether it's doing it correctly or not. But in this case, seems like the system is very sensitive to the teacher. So if the teacher imparts a bias into the learning, that is not so easy for third parties come in and say, well, is the psychopath teaching how the machine learns, and the machine therefore learns bad habits, and so forth. How does a third party come in and see whether there is a correct or incorrect learning from a particular system?
Right. So that's certainly a problem, and even before we had machine learning systems, we had this phrase of garbage in, garbage out, and so if you train it on the wrong thing, it's going to learn the wrong thing. So that's certainly something to deal with. Now, your first part of your statement saying, if you have a traditional program, any programmer can debug it. In some sense, that's true.
Some better than others.
Right. But if it was really true, right, so if regular programs were really understandable and machine learning programs were not understandable, then there would never be a bug in a regular program, right?
Yeah, but
Because,
the assumption is deterministic.
yeah,
But there is a correct answer, and if you tell the observer what you intended to do, they ought to be able to track it.
right. So I think one thing that's important is figuring out when the uncertainty is in the problem versus when it's in the solution, right? And so you can only have determinism when there's no uncertainty in either, right? So say I wanted to write a program to recognize faces, I can do that in the traditional programming approach, but it's still going to be uncertain what the answer is. I show you this picture of
So you can make a distinction whether it's a bad program or it is a bad algorithm or the bad implementation of that algorithm. And it seems
That's
like
true,
it's
right.
more hidden in this case of the machine learning.
let's see.
Because
Right.
the correct answer is based on what the teacher says. Right? The teacher
Yeah.
says, you've got this
Right,
correct.
so you're saying somebody says, here's this algorithm for recognizing faces, you go code it up, right? And now there's two questions. One, does the code faithfully represent the algorithm? And secondly, how good is the algorithm, right? So we can divide those up. So in machine learning, let's see. So there, in some ways, we have some of the same kind of idea, right? So you have to encode a machine learning algorithm. We have to say, did we do this algorithm correctly? This is a deep learning algorithm, or it's a random forest, or whatever. But that part's pretty easy, right? Usually the bugs aren't there. Rather, the bugs are, I gave it this input data, and it did exactly what it was supposed to do, but the answers were wrong anyways, because the input data either didn't cover everything that it should cover, or it was actually wrong, right? It gave me, it's retrieving exactly what I told it to do, but it should have had something else.
Or in a learning system, it's answered only wrong if the teacher says it's wrong. And if you ask the machine to say, this is murder, and everybody has a different line of where murder is, and you teach the machine to be exactly what you tell it to learn, when is the machine wrong? When?
Yeah, well, so we haven't solved that for any system, right? Whether it's a computer or a courtroom, we still don't know where those lines fall.
Well, first off, as a current Cal student, go Bears. My question was actually along the lines of what was just asked, but it was specifically about the fact that, as you've mentioned, these sort of deep learning or just machine learning in general takes in a lot of data when it comes up with the models of how it views the world and how it solves its problems. And so as computer scientists, what can be done as the gatekeepers of what data is being used to ensure that the data being used is in fact like unbiased and like correctly labeled, because as you touched upon, it seems to require a lot of different sort of fields to kind of interplay, such as sociology, maybe psychology, maybe some philosophy if the questions are particularly tough. So I was just wondering what your take was on what like should be done in like the software industry in general to have that.
Right. So I think we're gaining experience in how to do that. And certainly, there's no one thing, right? So so the first step is, do I already have the data, or do I have to generate it? Right. Sometimes you're just given it, and you collect it, and then it's a question of analyzing it. Other times, like I said, you're acting like a scientist, so basically you have to design an experiment. Say, what experiment am I going to run to be able to collect that data? And for a lot of the high-tech companies now, those experiments are run over their users, and we say, we'll do this, we'll see how they respond, and then we'll build something off of that. And there the question, the problems are, well, one, maybe the users are lying to you, right? So we've seen that a lot, where people try to game the system. So as an example, we had a thing a while ago where in the Russian to Ukrainian machine translation, Russia was translated as Mordor. So how did that happen? Well, we built a system and we had a program where we said, if we make a mistake in translation, you can volunteer a correction. So it's sort of crowdsourcing this idea. And some hackers got together saying, we're going to put in this correction and we're going to make it come from lots of different places. So it seems like it's a common correction. Of course, we were smart enough to say, well, we shouldn't just accept any suggestion that comes in off of these unwashed masses. Rather, we build up this program over time. And we have some trusted, fanatic people who, you know, they really love their native language and they want to protect it. And they've been making judgments for years and they've been doing a great job. So we show all the new suggestions to them. And every time in the past, they've been very reliable. This time, they said, that's so funny, I'm going to improve it. So now we need a second level of tests on the testers.